In this video, we are going to talk about simply and multiply connected domains. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. We will start with the idea of a simply connected domain, which is a domain such that every simple closed contour within it encloses only points of the domain. We have this first picture here where we have a domain of a function shaded in green. This yellow portion outside of the domain is where our function is not analytic, so it is not part of our domain. But in this domain that's bounded by this kind of oval shape, you can see if we draw any closed curve, and I have one example closed curve here drawn in blue called C, that this simple closed curve will only contain points that are in the domain. It will not contain points where the function is not analytic. So this is a simply connected domain. A counterexample of a simply connected domain is this one here. So here we have our domain. It's kind of this circular shape with the middle part here, this middle circle, where it is not analytic. So now we can draw a closed contour, this closed contour C, such that it contains points that are not in our domain, where our function is not analytic. So this is not a simply connected domain. Related to the simply connected domain is the Cauchy-Gorsatz theorem. If a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. So this is an obviously useful theorem, and that it greatly simplifies the calculation of the integral. But what you need to know is that the function is analytic at all points interior to and on a simple closed contour C. Our next theorem is specifically about simply connected domains. If the function f is analytic throughout a simply connected domain D, then for every closed contour lying in D, the contour integral is equal to 0. So it's a more general result than the Cauchy-Gorsatz, which does not allow for the curve to cross itself. That is, a closed contour C can intersect itself a finite number of times because it consists of a finite number of simple closed contours. As in this example here, we have this contour that crosses itself several times, but you can see it's essentially piecewise made up of contour C1, C2, C3, and C4. And then we have this corollary. A function f that is analytic throughout a simply connected domain D must have an antiderivative everywhere in D. When we cover this topic in more detail after our overview, we will discuss this, and also I will remind you about the antiderivative theorem we had from our last video. Our next big topic will be multiply connected domains. A domain that is not simply connected is said to be multiply connected, and we have this theorem that says, suppose that C is a simple closed contour described in the counterclockwise direction. And then let's say we have more closed contours, C sub k, where k equals 1, 2, up to n. These are simple closed contours interior to C, all described in the clockwise direction, that are disjoint and whose interiors have no points in common. Then if a function f is analytic on all these contours and throughout the multiply connected domain consisting of the points inside C and exterior to C sub k, then this formula will hold. The contour integral over C plus the contour integral over all the C sub k will equal to 0. I have this tiny drawing here that we'll talk about in more detail, and also I'll make the drawing bigger. But here we have one curve C, and then we have these little curves C1 and C2 that are totally contained in C. And then we said the function is analytic throughout the multiply connected domain that consists of all the points inside C and exterior to C sub k. So inside C and exterior to C1 and C2. So it's this green shaded region. And again, what we're saying is the contour integral around C plus the contour integral going the opposite direction of C1 and C2 will all equal to 0. Last, we have our corollary, which is the principle of deformation of paths. So how often do you get to deform your path? And this is quite remarkable. So let C1 and C2 be denote positively oriented, simple closed contours, where C1 is interior to C2. So if you can imagine two contours, one inside the other. If a function f is analytic in the closed region consisting of those contours and all points in between, so f is analytic, then the contour integral of C2 is equal to the contour integral of C1. Even though C1 is larger than C2, their contour integrals will be equal. So that's quite remarkable, and we'll take a look at that. That wraps up our overview, so we're going to come back and take a closer look at the simply connected domain. A simply connected domain D is a domain such that every simple closed contour within it encloses only points of the domain. Our two pictures are here. Here's our picture of a simply connected domain. It's this D here that's bordered by this black contour, and it's shaded in green. So here, any closed contour we care to draw inside of D will contain only points in the domain. There's no way to draw some closed curve inside of D that also contains any part of this yellow part where our function is not analytic. We can contrast that with this drawing of something that is not a domain that is not simply connected. Here we have our domain inside this contour, this circular kind of contour, and it's shaded in green, but we have this middle portion here where our function is not analytic, so it is not part of our domain. So we shade that in yellow to indicate our function is not analytic here. So now in our domain, we can draw a closed contour that encloses points that is outside the domain, that is not analytic. So this is what makes this contour enclosing these non-analytic points is what makes this domain not simply connected. Again, there are interior points of C that are not in D. The first theorem we will look at that's related is the Cauchy-Gorsuch theorem. So if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. And we can use this picture to discuss this. So let's say we have this closed contour C. You can see it's in the green region where f is analytic. But in particular, this function is analytic at all points interior to and on the simple closed contour C. And for that reason, then the integral around the closed curve is equal to 0. Here in this not simply connected domain, we could have drawn another closed contour. Let me do this in red. That's the other picture I have. Let's say we have this C2 curve here. You can see that C2, everywhere on the curve and inside, is analytic. And therefore, the closed contour integral of C2 is also equal to 0. Even though this is not a simply connected domain. Next, we have this theorem specifically about simply connected domains. If the function f is analytic throughout a simply connected domain D, then for every closed contour lying in D, the closed contour integral is equal to 0. And this is a more general result than the Cauchy-Gorsuch, which does not allow for curves to cross itself. And to see a closed contour C can intersect itself a finite number of times because it consists of a finite number of simple closed contours. So this is our example. So let me just trace over this path. I'm going to start here. I can go around, and I've gone around C1. I can come over here to trace out C4. I can trace out C3, and then I can finish by finishing off C2. Now what we have then is the integral of our function around this entire intersecting closed contour is going to equal to the sum of each of the individual little simple closed contours. And by our theorem, each of these simple closed contours is equal to 0. And I have one other example to give you. If C is any closed contour lying in the open disk, with a radius of 2, so anything inside here but not including the border, then our closed contour of this integral is going to equal to 0, even though this function here does have two singularities at z equals plus and minus 3i. But you can see those singularities, they're over here. Oh, I'm sorry, actually, it's 3i. So it's up here at 3i and at negative 3i. And so since our closed contour is within where it's analytic, we can use our theorem and say the closed contour integral of this, anything inside this radius of 2 of this function will equal to 0. And that's what we have to say about our simply connected domains. These examples go really fast because the answer is equal to 0. You just need to see that your function and your domain meet the criteria. I take that back. We're not done with simply connected domains. We have one more corollary. So a function f that is analytic throughout a simply connected domain must have an antiderivative everywhere in D. This corollary adds on to this theorem we had in our video when we discussed antiderivatives and our first look at the Cauchy-Gorsatz theorem. The theorem said suppose that a function f is continuous on a domain D, then if any one of the following statements is true, then so are the others. 1, f of z has an antiderivative, capital F of z. 2, the integrals of f of z along the contours lying entirely in D and extending from any fixed point z1 to z2 all have the same value. In other words, the integral is independent of the path and only depend on the endpoints. This is an extension of the fundamental theorem of calculus. It's what you're used to seeing from first-year calculus, where when you integrate, you take the antiderivative and then just plug in the endpoints. And then C, we have the integrals of f of z around a closed contour lying entirely in D all have value 0. And that's because these endpoints are going to be the same if you have a closed contour. So then when you subtract your antiderivative of z2 minus z1, you're going to get 0. Now this corollary adds on to this theorem that we had seen in a previous video. This corollary says that a function f that is analytic throughout a simply connected domain must have an antiderivative. Along with this theorem, it also means that a function f that is analytic throughout a simply connected domain, then the integrals depend only on the antiderivative and the endpoints. Or a function that is analytic throughout a simply connected domain D, then the integral of f of z around any closed contour all have value 0. In summary, this corollary adds this condition about f being analytic throughout a simply connected domain to this theorem that we had previously looked at. Okay, now we're ready to look at multiply connected domains. A domain that is not simply connected is said to be multiply connected. Let's look at some examples and pictures, and hopefully this will be a little more meaningful. We have this theorem. Suppose that C is a simple closed contour described in the counterclockwise direction. So I've drawn C here, and it's in the counterclockwise direction. Now suppose we have C sub k, where k is equal to 1, 2, up to n, and I drew k equals 1 and 2, and these are simple closed contours interior to C and all described in the clockwise direction, and they're disjoint and whose interiors have no points in common. So here's my C1 in the clockwise direction, C2 in the clockwise direction. You can see they're disjoint. They do not share any interior points in common. If a function f is analytic on all of these contours and throughout the multiply connected domain consisting of all the points inside C and exterior to each ck. So I'm going to draw where we're analytic first. We need to be analytic on all these contours. So I outlined that in green. And throughout the multiply connected domain consisting of all the points inside C and exterior to C1 and C2. So we're analytic throughout this space here. So C1 and C2 essentially are contours that surround places that we may not be analytic. So I don't know if I really want to put this as yellow. These can be analytic, but they may not be analytic. So you know what? Maybe I'll crosshatch them as yellow and green. Maybe they're analytic, maybe they're not. But here we have this multiply connected domain here. And what we can say then is that the contour integral around C plus the contour integral around the C sub k, so the contour integral around C, the contour integral around C1 and C2, which are in the opposite direction, is equal to 0. To see why this formula is true, we're going to modify our drawing. We're going to modify our paths. First, we're going to add a line L1 to go from C to C1, and we'll draw this so that the path can go either from C to C1, or it can go the other direction, from C1 to C. We'll modify L2. We'll add an L2 to go from C1 to C2, and it can also go from C2 to C1. We'll modify by adding a line from C2 to C, and also this line can go from C to C2. Now what you can see is I have a simple closed curve that goes through all of these paths. So in other words, let's start here on C, and I'm going to come down around on C until I get to L1. I'm going to take L1 to go from C to C1. I'm going to follow the top of C1. Then I'm going to take L2 to get to C2. I'm going to follow the top of C2. Then I'm going to take L3 to get to C. Now I'm going to take L3 again, going the other way from C to C2. I'm going to follow the bottom of C2. Now I'm going to follow L2 to go from C2 to C1. I'm going to follow the bottom of C1, and then I'm going to follow L1 to get from C1 to C. And now I'm going to follow C the rest of the way around, all the way around till I return to my starting point. Now you can see that I have a single path that connects my C to my C1 and C2. But the other thing you'll notice is the lines that I added, the L1, L2, and L3 to connect everything. Every time I go from left to right, I also go from right to left. And since these paths are in the opposite direction, whatever my path integral is for this top, it's going to cancel with the path integral going back. So again, over here, for L2, first I went in the right first I went from C1 to C2, but then later I came back and integrated from C2 to C1. So these are the exact same path, the exact same function. The only difference is the direction. So they're going to have the same integral value, except this direction is going to be the negative of the other direction, meaning that when I add them together, they're going to cancel out. So even though I added lines L1, L2, L3, in effect, their contribution is going to cancel out, and I'm just going to be left with the path integral around C, C1, and C2. So relating that back to our formula, so because we have this one path that we had followed to get through this whole curve, and it's a closed path, then, and this is adding the L1, L2, L3, our entire path is equal to 0. But also we know that the L1, L2, and L3 portions of the integral are 0, so we can leave them out, which means that our integral around C plus the integral around C1 and C2 are equal to 0. And that's going to lead us to the principle of deformation, which is the corollary here, that if we have C1 and C2, they're positively oriented simple closed contours where C1 is interior to C2. So that's this picture here. Both are in the counterclockwise direction. C1 is within C2. If a function f is analytic in the closed region consisting of those contours and all the points in between, so we're analytic everywhere, then the contour integral of C2 will equal the contour integral of C1. This is really quite remarkable, but it follows directly from this work we did here with our multiply connected domains. That is, we can think of this C2 like this C that contains another contour, C1. The only difference is this C1 is in the opposite direction, so we'll have to remember to introduce a negative sign. But according to this, then our line integral of C2 plus our line integral of C1 going the opposite direction, so we put C1 in the negative direction, should equal to 0. And then if we want it in the positive direction, if we move this over and we also take the positive direction, then these two contour integrals will be equal. And another way of saying this, if C1 is continuously deformed until we get to C2, so we take this contour and we stretch it, we pull it, whatever, or we kind of shrink it, somehow we deform it until we eventually get to C2, always passing through points with f as analytic, so this doesn't work if there are points that are not analytic, but if it's always passing through points where f is analytic, then the value of the integral of f over c1 never changes. So we can deform c1 until we get c2 without changing the value of the integral. Again, that's really remarkable because you can deform your curve. You could be going around a tree, right? And if you can't parameterize your tree, you can deform this tree-like curve into a circle, which is easy to parameterize, or this oval, which is harder to parameterize. But generally, you'll try for a circle because it's easy to parameterize. No matter how complicated your C1 is, as long as you're in an analytic region, you can deform your path to become a circle. Your book has one example for this section. When C is any positively oriented simple closed contour surrounding the origin, show that the contour integral of 1 over z dz is equal to 2 pi I. I have a picture here. I have C, it's positively oriented simple closed contour surrounding the origin. The other thing to note, my function, which is 1 over z, is not analytic at z equals 0. I haven't been given enough information about C to be able to parameterize it. But I can use the idea of path deformation. So I can construct a positively oriented circle because I know how to parameterize those. I'll call it C0, with the center at the origin and a radius small enough that C0 is entirely inside my contour C. From path deformation, I know that the contour integral around C should equal to the contour integral around C0. Because I'm going to need more space, I kind of condensed things. I have my theorem here for your reference. I have the problem statement. When C is any positively simple closed curve surrounding the origin, show that the contour integral of 1 over z dz is equal to 2 pi I. So I've written that here. And I shrunk my picture of C0, which is within my contour integral C. If you remember from our last video about antiderivatives and the Cauchy-Goursat theorem, you might be tempted to try to use this theorem, although you do have a hint that it's not going to be applicable because Cauchy-Goursat would tell you that the integral around the closed curve is equal to 0, and our problem is trying to prove that it's equal to 2 pi I. So that's your first clue that Cauchy-Goursat is not applicable. But why isn't it applicable? It's because f needs to be analytic at all points interior to and on the simple closed contour. And here, f is analytic on the curve, but it's not analytic on all the points interior. In particular, it's not analytic at z equals 0. So Cauchy-Goursat is not applicable. We had this other theorem also when we discussed antiderivatives and the Cauchy-Goursat's theorem that said if we had a function that was continuous on a domain, and if any one of the following statements is true, then so are the others. And the first one was if f of z has an antiderivative, capital F of z throughout D, then that's equivalent to saying the integrals of f of z around closed contours lying entirely in D all have value 0. Again, since this would suggest that our contour integral would be 0, we know that this theorem doesn't apply. But why is the important question? And actually, we looked at this problem when we had our previous video on antiderivatives and Cauchy-Goursats. So let's take another quick look at that. So I replaced our theorem about simply and multiply connected domains over here with our theorem about the antiderivative. And here I had the example, which we had worked in our previous video. If C is the positively oriented circle that goes from negative pi to pi, and in this example, the radius was 2, then when we looked at f of z equals 1 over z squared. It was continuous everywhere except at z equals 0. And looking at our theorem, f of z has to be continuous on a domain. It doesn't say it needs to be continuous interior to any curve, but it says it's continuous on a domain, and f of z has an antiderivative throughout that domain. Then the integrals around closed contours all have lying entirely in the domain, and in this case, the curve lies entirely in the domain because essentially the domain is everywhere except at this one point. So, there's that little hole at z equals 0, but the curve lies entirely in the domain. So we can use this theorem. So the antiderivative of 1 over z squared is minus 1 over z, or in other words, f prime of z is equal to f of z. As long as z does not equal to 0, we can apply our theorem then and say that, it's this theorem here where the integral around a closed contour will all have 0 value. So we said if c is a closed contour, then 1 over z squared dz equals 0. And this is the example of how this theorem is supposed to be used. But our next example, again, we had covered this in our previous video about the antiderivative in Cauchy-Gorasatz, looked at f of z equals 1 of z, which is exactly the function we have in our example for simply a multiply connected domains. So we looked at f of z equals 1 over z. We said the antiderivative is log of z. However, the log of z is not a function, it's a multi-valued function. So it's not defined along its branch cut. So c does not lie in any domain throughout which f prime of z equals 1 of z, and we cannot make use of this antiderivative theorem, except that we were able to use branch cuts. And again, branch cuts was a video even before we had talked about antiderivatives. So it's been a while, but the branch cut allowed us to avoid these areas where a function is not defined. And what we did for 1 over z is we cut our circle into two parts. First, we took the right hemisphere and we defined our branch cut for log of z as the point from 0 all the way to the left on the x-axis. So in other words, now when we take our log, we can make log a single valued function where log is either negative pi to pi, not including negative pi or pi, because we're not along this line here. We're avoiding this line, but our log can take any value, and it's one value. It doesn't keep going around in a circle taking multiple values. So C1 is our principal branch, where f of z is equal to log of z. And remember, when we looked at log of z, the definition of log of z is natural log of r plus I theta, where r is greater than 0 and theta is between negative pi and pi, because we're on the principal branch. And that will serve now as our antiderivative of 1 over z. And then we were able to use now our theorem. So we had our 1 over z, we took our antiderivative, plugged in our two endpoints, which was this part over here, part B of our theorem, and we were able to get the answer pi I. To get the left hemisphere, or left circle, left half of our circle, we used this other branch cut. So we divided up our C0 circle into C1 here and C2 on the other side. Now we take the branch cut so that log now can be anything between the values of 0 and 2 pi. That's the branch we're going to use for our logarithm. Again, we take the antiderivative and then we plug in our endpoints and we got pi I. So in this example, our total contour integral is going to evaluate to pi I plus pi I, which is 2 pi I. And essentially we get the same answer. The only difference that we should be aware of is in the example for this chapter, we're working with radius equals r. We're not told what the radius is, and here we're using the radius 2. So if we substitute an r for the 2, and I'm going to do that now. So here, my radius I put in r because remember, we wanted a radius that was sufficiently small that it would be contained within our curve C. So we don't know how small it needs to be, but we'll just generically call it r. Then I substituted r for 2 and I put it in blue just so you can see where I made the changes. But you can see that eventually this natural log here cancels out with this minus natural log, so you're still going to get the same answer pi I. And that's similar over here. If you get rid of the 2 and replace it with r, you see that the natural log of 2 cancels with this natural log of 2, and you're going to get pi I for this half of the branch. So your total contour integral is going to be equal to 2 pi I. And to summarize this example, we used ideas from this chapter, the simply and multiply connected domains. We used the idea of branch cuts, which was covered in a previous video, and we also used this theorem, which came from a previous video where we talked about definite integrals and the Cauchy-Gorsatz theorem. So if this was kind of too quick, you might want to go back and review the other 2 videos on branch cuts and antiderivatives. To review what we covered in this video, first we defined a simply connected domain, which is a domain such that every simple closed contour within it encloses only points of our domain where things are analytic. We had this Cauchy-Gorsatz theorem: if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. And we have this more general theorem for simply connected domains. It's similar to Cauchy-Gorsatz or related, but it's more generalized. If a function f is analytic throughout a simply connected domain D, then for every closed contour lying in D, the contour integral is equal to 0. And we talked about how the closed contour here can intersect itself a finite number of times because we can consider it kind of the joining of a finite number of simple closed contours. So like here in this example, this is kind of a closed contour that keeps intersecting itself. Let's just trace it through. It goes through all the way here. It outlines C4. It outlines C3, C2. But we can consider this 4 different closed contours, C1, which then leads into C2, which leads into C3, which leads into C4. So we can consider this contour kind of a summation of our 4 contours. And we had this example here, which highlighted we could have this contour which intersected itself. It could even have singularities, but as long as the singularities was outside our contour, they don't affect our theorem, and we can apply our theorem and say that the integral around the closed contour is equal to 0. And we have this corollary: a function f that is analytic throughout a simply connected domain D must have an antiderivative everywhere in D. We then looked at multiply connected domains. So a domain that is not simply connected is by default said to be multiply connected. And we have this theorem that says if C is a simple closed contour described in the counterclockwise direction, and then we have these other simple closed contours, C1, C2, C3 up to Cn, that are interior to C, all described in the clockwise direction, the opposite direction, that are disjoint and whose interiors have no points in common, then if a function f is analytic on all these contours and throughout the multiply connected domain consisting of all the points inside C and exterior to CK, then we have this formula that applies that the contour integral along C plus the contour along the individual C sub k will equal to 0. And we have this tiny drawing here. C is our big contour. C1 and C2 are contours that go the opposite direction, totally inside our contour C, right? Because C sub k are all interior to C. Then what this says is the function's analytic, all points inside C and exterior to C sub k. So that's this green region. It's inside C but exterior to C1 and C2. Then our contour integral along C, going in the counterclockwise direction, plus the contour integrals along C sub k, along C sub 1, and C sub 2, which are in the opposite direction. So you add those 3 contour integrals and you will get 0. And perhaps the most useful and certainly the most interesting result of this is this principle of deformation of paths that says let C1 and C2 denote positively oriented simple closed contours where C1 is interior to C2. If a function f is analytic in the closed region consisting of those contours and all points in between, then the contour integral of C2 is equal to the contour integral of C1. Again, another fascinating theorem. Anyway, that's it for this video. Thank you for watching.